All right, we're ready to embark on the third and final day of section 2-2. We'll start with problem number 12. It's a cannonball, which is shot directly upward, which in itself is not the smartest thing to do, but hey, whatever. With an initial velocity of 35 meters per second, so that thing is moving. Its height at any given moment is given by S. Our book likes to use S for height. I know physics books a lot of times will use Y, which actually makes a little bit more sense, or sometimes just simply H for height, but math books like to use S. I don't know why. Personally, I think S looks like a 5, but hey, whatever. All right, so there's S equals. Physics people, you may notice what's going on here. If you're not in physics, just bear with me for a moment. That's a physics formula. Again, normally physics is Y equals. It's VIT. Some textbooks will call it VO for velocity original. Some will call it VI for velocity initial. It's the same thing. Initial velocity times t plus 1/2 gt squared. And g is gravity. That's the negative 9.8 meters per second squared. You can see that with 1/2, now you're down from 9.8 to 4.9. VI, velocity initial, by the way, is the 35 meters per second. That's VI. And then this plus 4 at the end, I'll just call it plus C, just tells me that this is shot off of a 4-meter high pedestal, even though the problem didn't say that. Because I've been in physics, I realized that. Okay, so that's just kind of interesting. What's really interesting, though, is I have that equation. You've seen already that the derivative of position is velocity. And when you take the derivative of VIT, it's just VI. Because think about it, the derivative of 2t is 2. The derivative of 5t is 5. The derivative of 35t will be 35. And when you take the derivative here, using the power rule, remember g is not a variable, it's a constant. Gravity doesn't change. I mean, yeah, if you're in Denver, it's a little bit lighter because you're farther from the center of the earth, but I mean, not by much. 2 times 1/2 will just be 1. It's just going to be gt. And the plus 4 at the end doesn't matter because the derivative of a constant is 0. So that's your formula for velocity. And your formula for acceleration is another derivative. VI, in this case, the 35 is a constant, so it's gone. And the derivative of gt is simply g, which means that acceleration due to gravity is a non-discriminating force. It doesn't care how old you are. It doesn't care about your race or your gender or where you live or anything. It's going to pull on you the same. 9.8 meters per second squared. Woo! All right, that's a physics moment. Let's backtrack. Okay, all of you who are not in physics, you can reopen your ears. I'm going to still teach physics, but I'm going to do it with a little bit of a calc feel to it, a little calculus slant. Here's the 4-meter high pedestal. Here's the cannon. It shoots a cannonball. I'm not shooting my cannonball directly upward. I'm not stupid. I'm going to shoot my cannonball like this. What's cool is if you shoot a cannonball directly upward, or if you shoot a cannonball out and then it falls, it's going to be in the air the same amount of time. And it's also going to reach the same height because in physics, horizontal and vertical components are independent of each other. Isn't that weird? If you take a gun, hopefully you aim it away from people, and you take the gun and you shoot it parallel to the ground, and in your other hand you take a bullet and just drop it, those two bullets will hit the ground at the same time. Usually you don't see it because the bullet will strike something or someone before it hits the ground. Plus the earth is curved, so every mile the earth curves 59 feet. There's a whole bunch of different things involved that you would never notice the bullets hitting the ground at the same time, but they would. All right, so I'm going to shoot the cannonball off like that. How long did it take for the cannonball to reach its maximum height? The maximum height would be right here. How long did it take? Well, maximum height means the cannonball hangs in the air just for a split second right there. You ever throw a baseball up in the air or a softball or tennis ball and you watch its trajectory, and then it starts to fall. Just for a moment there, it hangs, and its velocity is 0. It's not moving up or down. So when the question says how long does it take the cannonball to reach its maximum height, really it's saying, when's the velocity 0? And the velocity is the derivative of position. So the velocity, using our brand new power rule, 35t to the first, the velocity will be 35, which agrees with the physics formula. Let's see, now we have exponent times coefficient on the next term. 2 times negative 4.9 will be negative 9.8. T to the first, and the plus 4 won't matter. Its derivative is 0. So there you go. Now we want the velocity to be 0, so we're going to plug a 0 in here. Don't plug a 0 into time, because that means the cannonball is still in the cannon. Make sure the 0 gets plugged in where the V is. You add 9.8t to both sides, divide by 9.8, and time comes out 25 sevenths, or 3.571 seconds. All right, so it takes about 3.5 seconds to make it there. How high did the cannonball go? That's the next question. We've got a formula for height above ground. It's circled up there in blue, and we know what t is when we reach the highest point is 25 sevenths, so all we have to do is just plug that back in a couple places, use our graphing calculator to get the answer, and we're done. Okay, I copied the formula for height down, and we're going to plug in the 25 sevenths. The 25 sevenths is preferable over the 3.571 because that 3.571 has been rounded off. It's not really 571 at the end. There were other decimals that we ignored. And that's going to be an issue because if you plug that in here, rounding off is actually making a mistake on purpose. Is really what it is. If something at the grocery store is $2.99, you're like, $3. That way you know you have enough money in your wallet. But really you're overcharging yourself by a cent on purpose. Same thing here. If you take that rounded off thing and put it here and you're going to multiply it by 35, that's a bigger deal. So whenever possible, you want to use the exact fraction to plug in, the 25 sevenths, or you want to store this accurate to 9 or 10 places on your calculator before you reuse it. Otherwise, you're going to ruin the second answer, if that makes sense. So in goes the 25 sevenths. And then at this point, just let your calculator work this out for you. You don't need to do it yourself. And to my amazement, it came out exactly to 66.5 meters, right on the nose. Now, you can write 66.500 if you want to go to 3 places just to be safe, but since it's an exact value, it's okay to stop at 0.5 here in this case. All right, so that's how high it made it. Let's move on. When did this cannonball reach half of its maximum height? Well, obviously, half of its maximum height will be half of the 66.5 that we just found. So that's going to be 33 1/4 meters. So if this is 66.5, then 33.25 would probably be, I don't know, right about there. So it's going to actually happen twice, once on the way up and once on the way down. So we should expect to get 2 separate answers, and we will. Now keep in mind that this 33.25 is height, which is S. And we have a height formula already right here, remember? So we're just going to take it and we're going to plug it in right there. Don't plug the 33.25 in for time. Okay, plug it in for height. And solving this won't require calculus at all. This is simply a quadratic formula problem. Before you use quadratic formula, of course, you do need a 0 on one side, and you also need descending order, so I've got some rearranging to do. I'll subtract away 33.25 from both sides. That'll give me the 0 over here that I need, and right now I'll rewrite it in descending order as well. Again, using quadratic formula, and The expectation is you use your calculator. Please do not use these crazy decimals and do the formula by hand. If you don't have a quadratic formula program on your calculator, please let me know. I'll give you mine, or I can write you one from scratch if we don't have connector cables. But time is going to come out to be two things, 0.966 seconds and 6.176 seconds. So it took about a second to get here and a little over 6 seconds to get back over on the way down to the 33¼ meters high. All right, next question asks, we're not there yet, but it says, how long will the cannonball be in the air? Well, definitely longer than 6 seconds because it's still falling, probably 7 or 8 seconds. A lot of times I'd like to anticipate my answer before I get it. So I'm expecting 7, 8, maybe 9 seconds, probably closer to 7, because this thing is accelerating. All right, let's try that. Well, how long was the cannonball in the air means how long did it take for S to become 0? Because S is the height above the ground, and when S is 0, the cannonball makes impact with the ground. So again, this is another quadratic formula program problem. You just simply stick the 0 right in here. It's already 0, which is even easier. Again, you need descending order. And when you work that out, that's going to come out to two answers. Time is negative 0.113 seconds, and time is 7.255 seconds. And obviously the first answer is completely extraneous. That makes no sense at all. Actually, it does make sense. If I go back a slide to my picture, remember the graphing calculator does not realize that this is a cannonball. And so it's going to assume that the cannonball is on the ground at negative 1/10 of a second, and then it flies through the cannon and makes its path and lands at 7.255 seconds. So really, it does make sense with the graph, but since the cannonball starts here, this part never occurs. That's why I threw that first answer away. I'm actually really liking my second answer because remember I said I think it's going to be in the air for about 7 or 8 seconds, and so yeah, that makes sense. And finally, last but not least, how fast was this thing moving when it hit the ground? How fast was it moving? That's velocity. And we have a velocity equation. Maybe you remember what it was from a few slides ago. Maybe you don't feel like going back to a few slides ago. You could just get it again by taking the derivative of S. And the derivative of this thing, you may recall, is 35 minus 9.8t. Years ago, I taught out of a textbook, and they wanted people to do this derivative long form still. I'm like, that's just crazy. So I definitely try to teach you guys the power rule shortcut right away. Yeah, there you go. How fast was it moving when it hits the ground? A lot of people say 0, it hit the ground. I'm like, you really think a cannonball is going to hit the ground at 0 miles per hour? Would you like to be the test subject on that? Maybe you can stand on the ground and see if it conks you in the head at 0. I don't think you want to be that person. It's going to be in the air for 7.255 seconds. That's time. Pop that in and see what you have. Again, you're going to use your calculator. And when you plug those numbers in, and again, you're going to plug in not 7.255, you're going to plug in 7.255, 370,559. You want to keep this thing accurate if you're going to use it again. Okay, so have it stored out to 8, 9, 10 places, whatever your calculator takes. Plug that in, and you're going to get negative 36.103 after you round off. Now it says how fast was it moving, so you don't have to put the negative in your answer. If I ask for speed, then you must take the negative off. If I say how fast was it moving, you can say 36.103 downward in the downward direction, or you can leave the negative on. I'm not super picky. I'm going to take it off for this. But what you do have to have is units, and here the units will be meters per second. And again, that makes sense to me because this cannonball was shot out at 35 meters per second, but it had to cover an extra distance when it was falling. So remember, it came from a 4-meter high pedestal, and so it's going to actually fall a little farther than it rises. So it should gain a little bit more speed. So It goes out of the cannon at 35, it hits the ground at 36. Yeah, that makes sense. Now, I have to tell you, in real life, there's air resistance and a whole bunch of other things. There's friction as the cannonball's hitting air molecules. It's going to slow it down drastically. We're not going to get into mu values in here and all that physics stuff that, down the hall, they specialize in that. I'm just giving you guys the basics and kind of getting you started. So anyways, that's number 12. Whew, that was a long one. All right, back to particle motion. I can almost promise you a particle motion problem on the FRQ part of the APA exam. Seems like every year they do it. Okay, this particle moves along a line. Its position in meters is given by that equation, S of t again. Find the displacement. Displacement in science is defined as how far you are from your starting point. It's not total distance traveled. Again, I drive home every day. That's 17 miles for me. And I come back to school. That's another 17 miles. I probably go around town at least a little bit. I don't sit in my house all night. So I figure each day I probably put 40 miles on my car, 35 to 40 miles. But my displacement in 24 hours is 0. I'm right back here in room 700 teaching at Beechwood High School. So the displacement in the first 6 seconds will simply be S of 6 minus S of 0. What is S of 6? If you plug a 6 in here, you're going to get 36 minus 42 plus 10. That'll be 4. Minus. And I think it's easy to see if you plug a 0 in, you're going to get 10. And so the displacement is negative 6 meters. Remember, we're in meters here. I don't know exactly what this particle did. I don't know if it, vibrated back and forth or if it just went to the left leisurely 6 meters. But between start and finish, it's 6 meters to the left of where it started at. That's all I know. All right, part B here in orange. Find the average velocity during the first 6 seconds. Again, the word average signifies no calculus. All right, well, I know that it went 6 meters to the left, and I know that it took 6 seconds to get there. And so that means that the average velocity is simply going to be a division, and that's going to be negative 1 meter per second. That's all it is. Now we're getting into calc. I see the word instantaneous, which means, take a derivative. Instantaneous. So the derivative here is going to be 2t minus 7. That'll be velocity. Remember, the velocity is the derivative of position. And when you put the 5 in, that's going to make 10 minus 7, which of course is 3. And again, that's velocity, so it's going to be meters per second. So the average velocity of this thing was negative 1 meters per second. But at 5 seconds, it was heading to the right at 3 meters per second. So this particle is moving back and forth. It's not just going one way. Okay, that's good to know. Find the particle's acceleration when time equals 5. Well, acceleration is the second derivative. Remember, we had the first derivative already. That was velocity. So the acceleration would just be the next derivative, second derivative. The derivative of 2t, of course, is 2. Minus 7 is a constant. So the acceleration is 2. Now we have to plug the 5 in for the t. Oh, there aren't any t's. Well, that's because the acceleration's constant. It's always 2 no matter what the time is. So the acceleration at time equals 5, or any time, is going to be 2, but it's meters per second, or meters per second squared. Part E, at what values of t does the particle change direction? We know this thing changes direction at least once because we know that its overall velocity, its average velocity was negative 1, but yet we found it moving to the right at 3 meters per second. So we know it's going back and forth. When does it change its mind? When does it change direction? Well, things change direction, just like the cannonball, when the velocity is 0. You think about it. If you're jogging forward and you turn around and you jog backwards, for a brief fleeting moment in time, you have no velocity as you're changing the direction. The velocity is 0. I have a velocity equation already. right here. So I'll just set the velocity equal to 0 and bring that down. Again, don't set time equal to 0. Set velocity equal to 0. So we have the 2t minus 7. That's equal to 0. I don't think you have to be an algebra genius to figure out that time is 3.5 seconds. Or 7/2 if you're a fraction fan. Finally, part F. Where is the particle when the position is a minimum? In other words, in plain simple English, where's the particle when it's farthest to the left? How far to the left did it make it? Well, it only changed direction once. Between 0 and 6 seconds, it changed direction at 3.5 seconds. I know that it started at 10, because if you plug the 0 into the original equation, remember we got 10. And I know that at the end, it ended up at 4, because if you plug a 6 into the original equation, you may remember we got 4. All right, so here's a quick picture of this scenario. Here's the particle starting at 10. 6 seconds later, it ends at 4. But the motion that you saw me just do is incorrect because it changed direction at 3.5 seconds. So one of two things happened. Okay, let's take it back to the starting point again. It either started to the right, 1, 2, 3.5, changed directions, 4, 5, 6, and ended. At which case the answer would be 4. Where's the particle when the position's a minimum? Well, right where we ended. That's one possibility. Or, again, the starting point was 10. Maybe it shot out to the left right away. 1, 2, 3, 3.5 seconds, then turned around, 4, 5, 6. In which case, the answer is going to be even farther to the left. So I don't know which one of those cases is the true case, but I can figure that out. And here's how we know. Let's take the velocity right from the start. Again, I started at 10. Let's take the velocity equation up here in yellow, that I'm circling in red, and let's make time 0. You can see that the velocity would be 0 minus 7, or negative 7, which means when we say, and go, this particle takes off to the left. Okay, so it is case number 2. So to the left for 3.5 seconds, turns around, comes back, ends at 4. All right, that's cool. So how far did it make it to? What's this location that it turned around at on its journey? This is what we want to find. Well, that's easy enough. We have the original equation. I know it turns around at 3.5 seconds, so we can dump the 3.5 directly in. 3.5 squared is going to be 12.25. 7 times 3.5 will be, oh boy, minus 24.5. Plus 10. Why am I doing this mentally? Oh, well, hey, it's good for me. It's going to be negative 2.25 meters. So that's the turnaround point, and that is where the particle was when its location, S of t, was a minimum, farthest left. Made it up to negative 2.25. All right. This number 14 is a fabulous quiz question. I mean, and I would know. Hint, hint, if you know what I'm saying. It says the position is given by that equation. Find the speed of the object when its acceleration is 0. Oh, this is fantastic. Remember, first of all, that speed is the absolute value of velocity. So speed has to be positive. So if the velocity comes out negative, you need to realize that you need to take that negative off. Do you think on a test or a quiz I would make the velocity come out negative? Oh, you bet I would. Are you kidding? I want to see if you know. All right, let's see what happens. So we have our position equation up here. We want the speed, which means that it would make sense to find the velocity. So we'll take a derivative. That'll be our velocity equation. The derivative up here is going to be, using the power rule, be 6t to the second, exponent times coefficient down by a power, minus, again, 24t to the first, plus 17. Okay, that's the equation for velocity. That's where speed's going to come from as well. But we find the speed when its acceleration is 0. The acceleration is the second derivative. So the second derivative is going to be 12t minus 24. And we set the acceleration equal to 0. Again, not the time. Don't put the 0 here. Put the 0 here. All right, well, if 12t minus 24 is 0, I think you can see that time would be 2 seconds. Now, we want speed. And speed is related to velocity. So when you take this 2 seconds, don't plug it into the red original S equation. Plug it into the green. 2 is going to go here, and it's going to go here. So the velocity at 2 seconds is going to be, let's see what this is, 6 times 4, that's 24, minus 48, plus 17, and it's going to end up being negative 7. Now we want our units, which of course are going to be meters per second. Okay, now I warned you about this. Speed's never negative. Okay, so if this is a 4-point test question, I'll give you 3 out of 4. I'm impressed. You took 2 derivatives. You knew what you were doing. Get rid of that negative. If I ask you for the velocity, you have to have the negative. If I ask for speed, it better not be there. There, that's a great answer. Okay, remember, speed is always positive. Or maybe 0. All right, one more problem. We've done some physics. Let's get into some econ. We're covering the whole school here today. If you've taken econ before, maybe you know this already, but there's something called marginal cost. There's also marginal revenue. There's a few marginal things. Marginal means if we make one more unit, how does that change things? Let's say we're in a shoe factory. Let's say you're the CEO of a shoe company, and somebody's got to be it, right? And so the factory churns out 100 pairs of shoes in a day, and it costs $4,000 to make all those shoes. You've got the materials, the leather, the laces, but you also have people involved. You have workers that you need to pay, machinery that you have to purchase and maintain. You have your factory that you have to pay the rent on. You have to pay the utilities. You need water in the plant. You need electricity. Can't make shoes in the dark. Altogether, your total costs are $4,000. But you made 100 pairs of shoes, so each pair of shoes is going to cost you $40 to make. All right, in our capitalist society, what you do is you make them for $40 a pair. You sell them to a sporting goods outlet for maybe $60 a pair, and then they charge the customer $100 a pair. And everybody's happy. All right. But what if it was the end of the day and you're like, oh, let's make one more pair of sneakers for my granddaughter. She's right here. She's so cute. And they're like, all right, fine. The people are already there. The machines are already turned on still. You've already paid your electric bill. We'll just make one more pair of shoes. Well, that pair of shoes is not going to cost $40 because, like I said, everything's already up and running. People are efficient. It's only going to cost $31. And that's called the marginal cost for that last pair of shoes. And really, this illustration explains the whole premise behind Sam's Club, BJ's Wholesale, and Costco. The more you buy, the cheaper it is per item because of, efficiencies in the workplace. All right, so we're going to find marginal cost. And the cool thing is, to find marginal cost, use the derivative. Oh, yeah. Derivatives in econ. All right, this is the last problem. We're going to do number 15. It's got a part A and part B. Part A says find the average cost. And again, the word average means don't use calculus. And then part B wants the marginal cost. Here we will use calc. And then we'll be all done with section 2 too. We'll wrap it all up. Okay, back to part A. Find the average cost of producing 100 computers. Well, again, average just harkens back to middle school slope. So we want the cost of making 100 minus the cost of making 0 over 100 minus 0. That's like y2 minus y1 over x2 minus x1, except the y's are computers instead of y's. They're c's. All right, if you make 100 computers, how much is it going to cost? Well, you have to put the 100 in here and in here. Let's see what that comes out to. And I'll tell you what that comes out to. It comes out to $44,000. All right, minus. What's the cost of making no computers? And at first glance, people are like, oh, 0. Oh no, there's a cost. If you have the employees come in and you're like, hey, we're going to make no computers today. Everybody's like, what? And you roll open the secret back door to the warehouse and there's like, cornhole back there and pizza and stuff. And they're like, what? And you're like, we're having a party. We're not going to do any work. Your employees are like, oh my gosh. But you still have to pay the rent on the building. You still have to maintain the machinery. You're still paying the electric bill. It's still going to cost you $5,000 to do nothing. I mean, the employees are going to want to be paid still. Can you imagine, like, after the pizza party's over, you break the news to them, they're like, by the way, we're not paying you for today. They'd be like, what? It's not cool. So it's still going to have a cost. In the denominator, 100 minus 0 is simply 100. All right, so subtraction, that's going to make 39,000 over 100, which will come out to $390 per computer. So you can crank out a typical computer for $390. You sell it to Best Buy for $500, and they sell it to you for $900. Retail. Nice. It's the American way, man. All right, so $390 is the average cost. But what if you wanted to make just one more computer? Just one more. Do you think it's really going to cost you $390 to make that 101st computer? Probably not. The electric bill's already paid. Your workers are already paid. They can stay for another 2 minutes, 5 minutes, whatever it is. So marginal cost does use calculus. And actually, I think it's even easier than the red part that we just did with average. That's cost prime. Little prime sign there. What's the derivative of 5,000? Well, it's 0. It's gone. And doesn't that make sense? I mean, your electric bill's paid. Your workers are paid. That's not going to matter. The derivative here, though, will matter. That's 400. And the derivative here is going to be negative 0.2 x to the first. All you have to do now is take the 101, plug it in. And that's going to come out to $379.80. So you can see that now that we're an efficient machine, we can start making computers a little cheaper. Sure, the average cost was $390, but now we can give you a computer for $380, save you $10, actually $10.20 discount. So that's the marginal cost, the cost of producing just one more. And you can find the marginal cost of the 102nd, 103rd, 104th computers. You can see that with the minus in front, right here, as these numbers go up, it's going to be cheaper and cheaper to make them. So again, that's why the big box stores can offer discounts. All right, that is section 2.2. We've done a ton of things. Before this section started, we didn't know the relationship between velocity and acceleration in original. We didn't know the shortcut power rule. We never really saw a chain rule before. We've done a little bit of trig derivatives. We've done a whole bunch of stuff, a whole bunch of physics, even a little bit of econ. Man, that's a lot of stuff. So again, if you need some help, a little extra help, or you have questions, don't be a stranger. Come find me or find me virtually if you need, and we'll work it through.